Hi and welcome back. So in the previous video, we introduced the concept of expected present discounted value. We also formulated or computed the general formula that is used to calculate this future expected present discounted value. So while we had clearly outlined the general formula, and it is quite simple to understand, it is, however, very useful to go through some examples to further understand its application. So this is what we do in this video. So to focus on the effects of the sequence of payment on the present value, let's assume that interest rates are expected to be constant over time, such that the interest rate now is equals to the future expected interest rate. And we denote the common value of interest rate by just I, which represent both the current interest rate as well as future interest rate. So the present value formula in this case is now given by this. So in this case, you would see that unlike before, the interest rate is uniform throughout the discounted values, with only a multiple of the earnings as the years go by. So in essence, in this case, the present value is the weighted sum of the current and expected future payments, with weights that are declined geographically through time. So if the weight of payment this year is 1, for instance, the weight on the payment in the n years, in the number of years from now, is given by this, or rather the discount factor of the number of n payments is given by this. So with a positive interest rate, the weight get closer and closer to 0 as we look further and further into the future. So an example is given here such that with an interest rate that is equals to 10%, the weight on payment 10 years from today is equals to 1 divided by 1 plus the interest rate of 10% to the power 10, which is 0.386. So that the payment of 1,000 rand in 10 years is worth 1,000 rand times the 0.386, which is 386 rand today. And the weight of payment in 30 years is given by 1 divided by the 1 and plus the interest rate of over 30 years, which is equals to 0.057. So that the payment of 1,000 rand 30 years from today is worth 57 rand today. Okay, so what about in a case where the constant interest rate and when there are constant interest rate and constant payment together? So in some cases, the sequence of payment for which we want to compute the present value is quite simple. For example, a typical fixed rate 30-year mortgage that requires a constant rent payment over 30 years. Consider a sequence of equal payments, and we call these equal payments RZ, without a time index over n years. So with our example, this is over n years, but including this year. So in this case, the present value formula is given by this equation, which basically shows the constant payment as well as the discounted factors over the years. So because the terms in the expression in the brackets represent a geographic series, we can compute the sum of the series and get to this equation here. So this is an equation that would use in a case where maybe, for example, you suppose one has won a 1 million rand from a lottery ticket, and they are presented with a check of that 1 million rand. So afterwards, you are told that to protect you from your worst spending instinct, as well as from your many new friends who want your money, they will pay you the R1,000,000 in equal yearly installments of 50,000 rand over the next 20 years. So now, what is the present value of your price today? So taking, for example, the interest rate is say 6% per year. The equation here will tell us that the V is given by 50,000, which is the sequence of payment over the years, into 0.688, which is the fraction here on top, divided by 0.057, which is the fraction below. And your present value of your million paid over 20 years in 50,000 sequence of payment will be equals to 608,000. So while this is not too bad of a winning, it is, however, less than $1 million in total. So you would have made less than $1 million. So this is the present value of R1,000,000 paid over 20 years in sequence of payments of 50,000 rand with an interest rate of 6%. Okay, so let's go one step further and assume that the payments are not only constant but go on forever. So it is hard to come up with real life examples of such a case. But one example comes from the 19th century England, when the government issued consols, which were bonds paying a fixed yearly amount forever. So let's let RZ be the constant payment. So if you assume that the payment starts next year rather than right away, as in the previous example, would get that from equation 14.7. We'll have this one. So this basically shows a heavily discounted or weighted sequence of payment, which is RZ, and it's discounted by these discount factors. So this is basically computed from a discounted multiple discounting factors of the RZ, such that 1 over 1 plus I to the power 2 RZ, and so on and so forth. So we can also take a few steps to simplify our equation, and the steps are given in the application of the proposition 2 in the appendix 2 in the end of the book. So our simplification and lookout of our formula is given by this equation here, which is basically a geographic computation of this, which is the same as the one I just made there. So this equation basically tells us that the present value of a constant sequence of payment RZ is simply equals to the ratio of the RZ and interest rate. So this is quite straightforward, because it suggests that the value now of this amount is equals to that amount and the impact interest rate has on. Since we said the sequence of payment is fixed, then it will only be affected by the interest rate. Hence we say its present value, it's the impact that interest rate has on it. So if the interest rate is expected to be 5% per year forever, the present value of the console that promises 10 rand per year forever equals to 10 rand divided by 0.05, which is the interest rate, which will be equals to 200 rand today. So if the interest rate increases and is now expected to be 10% per year forever, the present value of the console decreases to 10 divided by the 10%, which is basically 100 rand. Okay, so there's also a case where the interest rate is 0. So if interest rate is 0, then this fraction will be equals to 1, because simply this will fall out and it's going to be 1 divided by 1, and so will this one, and for any power of any years, for any number of years. So for that reason, the present discounted value of a sequence of expected payments is just the sum of those expected payments. Okay, so far we have computed the present value of a sequence of rent payments using the nominal interest rate. That is the interest rate in terms of rent. So we've specifically written our nominal, our present discounted value in terms of equation 14.6, which shows nominal interest rate. But now suppose we want to compute instead the present value of a sequence of real payments. That is payments in terms of the basket of goods rather than in terms of rent. So following the same logic as the one of the nominal interest rate that we've computed in the previous video and this one, we need to use the right interest rate for this case. So namely interest rate in terms of the basket of goods. So this is the using of the real interest rate. So specifically, we can write the present value of the sequence of payment as follows, which is the same as before, but now using a real interest rate and real expected interest or expected real interest rate. So in this equation, the RT and the R expected T plus 1 is the sequence of current and expected future interest rate. And the Z and the ZEs and whatnot is a sequence of current and expected future repayments. So these ones here. And VT here represent the real value of future payments. So an alternative way of calculating the real expected future present value of a sequence of payment is to obtain the expected future payment by constructing of the nominal one that we use in equation 14.6 and dividing it by price. So you can get the nominal expected future value and divide it by price to get the real values of the present discounted value of a future sequence of payment. So this computation of the real present discounted value will get you the same number or the same amount as using the equation where you use the real interest rate instead of the nominal interest rate. So what does this mean? It means that we can compute the present value of a sequence of payment in two ways. So one way is to compute it as the present value of a sequence of payment expressed in rents, discounted using the nominal interest rate, and then divided by the price level today. And the other way is to compute it as the present value of a sequence of payment expressed in real terms, discounted using the real interest rate. And you will see that the two ways will give you the same answer. All right, so this is where we are going to end our chapter 14, and we'll start our chapter 15 in the next video. Thank you.